You remember last time we have seen an example to in order to show you how we can optimize trajectories. And again, the concept of trajectory or trajectories is a concept not necessarily related to the movement of an object, as last time. Uh, is a topic, I would like to say, related to how it changes in an optimal way the states of a system. It doesn't matter if it's a chemical system, economical systems, could be everything. Of course, the more natural way to present this is to consider it in a dynamical system in the sense of mechanical systems. Um, and in fact, you remember, I considered the travel between Lüneburg and Hanover, for instance, in which I consider, I don't remember exactly well, but I think the position trajectory was in a parable in which we fixed the time and the final position, Hanover. Uh, and of course, we have a free parameter for the optimization. Now, the same problem, let me open the presentation, which I will upload later. The same problem in the sense, the same travel, but a different problem in the sense of constraints, I will present today. Let me. I don't know if I am able now. Yeah, no. Very shortly. Look, so we can reconsider a little bit the problem last time, but a little bit more, I don't want to say complex, but more articulated. I would like to travel from Lüneburg and Hanover. Now, look, here on the right, we have the data at the end. We can see the data of my system, mass of the car. We can see here friction factor, radio of the wheel. We can see that I try here to show you at least conceptually. I can give you the software if you need for your project. Today I don't want to go in depth in the software, but I have nevertheless the software. I can show also quickly the software a little bit because I copied the MATLAB code here, but I have also let me say the real MATLAB code. Yeah, we can see from these parameters that we are considering a linear system again as last time, because we can see that we characterize the friction just using a constant kf. Then it's interesting because we can see that I put now something more. We have the radius of the wheel. We have an electrical motor, which is characterized by a constant Ke. In some books, the Ke, the name is C phi factor. Anyway, it's something which allows to say is a factor which connects the electrical with the mechanical one. No, we can see from the unit. It should be here from the unit. Newton multiply meter divided ampere. This means if I multiply by the current, we obtain the torque. Just to understand. L in the inductance, R is the resistance, and then we have the gear ratio. And then we sum up, which sum up different things, no? Because we have a axis ratio and of course wheel and also the gear. But also, if I consider more than one gear, this parameter is represented by a set. These parameters it must be considered a set. This could be a nice project in order to also to include also the gears. But anyway, it's too complicated to explain now. I have also advanced results doing by students, of course. I mean, in the project, we can think together how we can extend 2 years, 3 years, and so on. In the optimization uh, of the trajectory, because of course depends also on the gears, because the gear changes. Do you remember the example last time? The force. Now, in the example last time, I didn't tell you about the torque, because do you remember it was just the mass which is moving. More abstract than this. More abstract than this. And then we will see what is the meaning of this cost factor. Look here. It seems to be a little bit difficult to be interpreted, because I copied the MATLAB file, or the MATLAB, parts of the MATLAB file. But again, if you are interested in such kind of optimization, also for your project, again, not necessarily must be a movement, a mechanical movement. Could be any kind of changes of states. Therefore, I told you chemical systems, economical systems, everything which I want to track could be, must be, or should be optimized. Do you remember why this problem? This problem in the context of optimization is important everywhere, which we have a track problem. The track problem is the most important problem. Do you remember MPC? In MPC, we calculated the optimal control law, but also should be interesting, should be more effective if the trajectory is also optimal. You remember, I didn't tell you about the trajectory. The trajectory could be everything. In MATLAB, we simulate with a trajectory towards an exponential trajectory, something like that. But it is optimal. We didn't tell you. I didn't tell you about the optimality. Here, we have seen, in accordance with the system, which we have to consider, this movement. Also last time, in MPC, we have seen, before last time, we have seen in the movement, what is the movement? The movement was an electrical motor without wheels, anyway, the movement was electrical, the electrical motor which change the two states, the output was the velocity, to track a particular profile of the velocity. Also, this implies also a particular current as a result. Here, you remember last time, we have seen that the calculation was to calculate the force, but in accordance to a particular condition on the travel. And then, as the consequence, we calculate also the optimal omega. Could be used, this omega could be used in the reference trajectory for the MPC. Look here, the problem is a bit more complex, not only because I have the wheels, I have an electrical motor, these aspects complicate, of course, the system to be considered. But look, with respect to last time, we can see here that we have a starting position, which is given. Last time was not given, I think was given, Lüneburg. We have a final position as last time, Hanover, for instance. Then we have a starting velocity and a final velocity. We have basically 4 constraints. This means, remember the concept which I tried to clarify last time. If I have 4 constraints to be optimized, we need to parameterize the trajectory using at least 5 coefficients. Because we need at least 1 coefficient free, let me say free, to optimize. Because if I don't have something free to be optimized, I have just a fixed trajectory, a fixed velocity, and this sense, a fixed acceleration. Look, in accordance of this concept here, if we want to parameterize the trajectory using a polynomial, why that? Because, at the beginning of the semester, I don't know if you remember, I told you about this polynomial optimization or parameterization, better to say. But of course, you can use any kind of of functions. Also, you can use combination of exponential functions. You can use wavelets. You can use Bezier function. You can use Bernstein polynomial. Anyway, any kind of, let me say, functions, but we need at least 5 coefficients, because 4 coefficients are, let me say, busy to satisfy. Now we can see together what I intend with the word busy, to satisfy these 4 conditions, and then we need at least one to optimize. About the word at least, we will discuss a little bit later what I intend. I told you also last time a little bit. Do you remember when I told you we can consider also a polynomial order 3? But let me go ahead with this, so we sum up with this slide what we did last time. Assuming that I want to work with a polynomial. This means we need a polynomial with 5 coefficients. 1, 2, 3, 4, and 5 coefficients. This means basically that we need to remember the number of coefficients is 1 more with respect to the order. This means, in this sense, if I need 5 coefficients, I need a polynomial order 4, because a polynomial order 4 consists of 5 coefficients. In any case, if you use a different functions, for instance, exponential function, we need, in any case, at least 5 exponential functions with different coefficients in this sense. The combination, let me say, of these functions. Coefficient, which one? The exponential, the exponent coefficient. Okay, let me try to explain this part of the software. Do you remember sims? I don't know if I told you the sims. This means in MATLAB you define after sims this element here, this basically 5 coefficients starting from A0, which we need to characterize the polynomial, and then we will see what is the parameter t, which is the time. Ig very quickly is basically the gear parameters, because I think here is not necessarily a parameter to be optimized, etc., but could be also the software used to optimize also the gear. But let me go ahead without considering too many parameters or too complicated concept at this moment. Look here. As I told you, we have a polynomial order 4, which is characterized by A0 plus A1 multiply T. Please pay attention here. I put T0 for a different reason, which I clarify in 1 second. Plus A2 multiply T up to 2, excuse me, or the T squared, plus A3 multiply T up to 3, plus A4 multiply T up to 4. Then, as I told you very quickly, at time T0, which could be considered 0, we are at the starting position. This means in Lüneburg. This means this in Lüneburg is F1 could be also 0. This means basically here I can write 0 equal what? A0, parameter which must be calculated. A1 calculated T0, which is 0, so T0 could be 0, and so on. This means we can see here that A0 is directly calculated by this condition here, which could be 0, could be 0, because at time 0, T0 could be 0. F1 is also 0. F2, which is the final position. This means in meter, 100,000 meter, it doesn't matter, no? And the value equal A0, which is 0, and then A1 multiply T1, which you remember I told you was 1 hour, no? We can see it. 3,600 seconds. Of course, this is in a condition. Is in a condition in which A0 is known And we have to write 100 kilometer, as I told you before, uh, equals A1, which must be calculated, multiply 3,600, and so on. T1 is no, is 1 hour. I can do the same consideration for the condition 3, let me say the condition 4. This basically is related to the velocity, starting velocity and final velocity. Assuming that F3 is also equal 0, this means at time 0, T0 in Lüneburg, we can see from here that A1 is also 0. What is this expression here? This expression here is the general expression of the velocity. In fact, you can see that this expression here represents the derivative of this. I mean, this is the trajectory from which I want to calculate from Lüneburg to Hanover, parameterized by these 5 parameters. This expression here is, I don't know if let me see if I find the software, it could be probably easy to open also the software to explain this problem through the software, or at least with a combination of the software and the presentation, instead of just the presentation, because in the presentation I summarized the most important part of the software, but it could be that in the software, if I remember well, I have more detailed. Let me see if I find it. Could be, I think, could be useful, because it could be that I have some comments. This means we can understand better. Let me see if I find. One second. Anyway, we have these conditions, but 4 conditions and 5 coefficients to be calculated. This means we have a coefficient 3. This means with these 4 equations, we can calculate one of these coefficients as a function of the parameter. Do you remember also last time of the model? And now I will show you a little bit more in detail. I hope that I can open. And then using, in this case, the derivative. Yeah, now I have it. We can calculate a parameter, the parameter phi, which allows to calculate all the rest. Let me show. Okay, let me see. Optimization. Okay. Okay, let me see. Here's just the LaTeX. Huh. Okay, let me see. Let me see. It could be that I found it. Let me share now. I hope. So we can combine both, no? The presentation with the software. It could be that in the software I have something more. Yeah, of course, of course. The software should work, no? We can see here's the data which I told you, no? Starting position x0 equals 0. This is more clear what I intend. Final position 100 kilometer. We can see here in the MATLAB language, 100 kilometer. We can see also, I will upload also, this could be useful again for any kind of trajectory tracking. No, 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 not necessarily in a mechanical, in the sense, tracking, let me say so. Here it seems that I put a lot of conditions. We can see also initial acceleration, but I don't know if I used. Let me say because let me say because I don't know if it's exactly our example. It probably yes, because here I put some condition more, but I don't think so that I used. Of course, if I put in a condition more, this means I have to increase the order of the polynomial, which I need in a polynomial order 5, not only order 4, if I include also the initial acceleration. This means acceleration 0 at the beginning means I will start softly, without jerk effect. Also, if I include Moreover, if I include in the final acceleration 0, again, we have a more soft landing. Of course, I need polynomial or the 6 to satisfy all conditions and to optimize. And I told you about the condition. I don't need to, yeah. Let me see what I have here. I have exactly here implemented the example of the presentation, because we can see here that you have these 4 conditions, but the condition number 5 related to acceleration, I commented. Yeah, then you can see here what I did, that I built here an algebraic system with the condition which I have. Yeah, this means with the function solve, which basically solves this algebraic system, which states the initial and final condition in terms of, in this case, position and velocity. Of course, without acceleration. Otherwise, I need to include the acceleration as a condition, and I have to consider an higher order of the polynomial. Here, I try to solve. If you want, I can try to run, but we will see. Exactly. Let me see. That could be nice if I run. I don't know if this works. I hope yes. Takes time. I don't know if I share. This is the problem now. Excuse me. Probably I didn't share. I don't remember. Let me share. Yeah. I think now I shared. I don't know if I shared. Yeah. Yeah, it seems to be this working. Let me show you what this equation is. Let me see. Yeah, look. In accordance with the condition, I have directly, as I told you before, A0 equals 0. Do you remember the initial condition considering T0 equals 0 at Lüneburg F1. Excuse me. F1 equals 0. We can see here, excuse me, I have to stop a little bit because I have to drink and I come back. Just let me stop the recording because I'm not able to continue. 5 minutes, I try to drink something and I come back. Excuse me just a second. Yeah. Ready, excuse me again for this interruption. Yeah, here basically we can see uh, the conditions, the four conditions. One is here, calculated at time 0 with F1 equals 0. 0 is our Lüneburg in this sense. The second condition is the final position. We can see at time 1 hour, no? A0 is 0, but we will calculate it by, we will see by the function solve. This is just equations one. Yeah, equation one is just the structure of the four equations in five, let me say, unknown. This means that each unknown can be calculated as the function of this fifth parameter. Anyway, we can see that here we have the second condition. Let me see where is finished. Yeah, here, no? Of course, 100 kilometer, no? Or the 100,000 meter, which we have basically the calculation, yeah, of the position at time 1 hour, 3,600 seconds for the condition which we have in Hanover, let me say. Then, comma, then we have the two conditions on the velocity. This means I do the derivative of the position. Therefore, we can see that the order, in the sense, is not visible the order because at time zero remains A1. At time zero remains, I write directly what remains. At time zero remains A1 equals 0, Lüneburg. And then here that, because the velocity in Lüneburg was 0, I start in with velocity 0. And here is the final velocity in Hanover. We can see that the, let me, yeah, exactly. The order of the polynomial is 3. Because we have here the parameter just until A4 in the position. We can see here. I don't know if it's visible from here. You have any comment? Uh, it's not very well. Probably yes. Let me see. I know it's the same. Like, but we can see from here. No, that's the order is 4 as long as I speak about positions, Lüneburg and Hanover. And here, when I speak about the velocity, we reduce the order. Velocity. Okay. Then using the function solves, let me say, solves of this system and a symbolical solution. If you look for a solution for the S, we can see the solution. We can see that the solution A0 equals 0, as I told you. A1 equals 0, I already justified, no? Initial velocity, initial position, initial velocity in Lüneburg. And look here, a parameter A2 or A3 can be calculated as a function of A4, both. This means A4 is the parameter which I can use to optimize. As last time, do you remember we did something similar? And then we have A2, I have A3, and then I can build my trajectory in terms of position and velocity. Of course, we will see I can calculate also the force which should generate the electrical system. I think we can continue here. I don't know, let me see in the presentation, because the idea was to combine the presentation with this. Let me see. It's a little bit too small, but let me see. Yeah, it's not so easy to see. But anyway, what we have here is exactly what I told you until now. No? We have the solution S. In particular, we can see here S2, S related to A2, as a function of A4. No? Again, mathematically, we have a system, an algebraic system with 4 equations and 5 coefficients. This means we can parameterize the coefficients, all coefficients with respect to one of them. I considered here A4, let me say, as a free parameter. Of course, in this particular case, we have A0, A1 equals 0. It's suitable in this sense, comfortable. And then again, A3 equals this expression here. Now, I can write, now it could be nice now proceed here. I can write the expression of the position as a function. Originally, do you remember? The position is a function of A0, A1, A2, A4, but A0 is 0, A1 again 0, but A2, let me see again here, no? A2 and A3 can be written as a function of A4. This means here we have a function here is 0, 0, plus a function of A4, which is here, which multiply t up to square. This expression here is again a function of A4, which multiply t up to 3, and then here A4 multiply t up to 4. This means the position, and of course also the velocity, we can see from here, are parameterized by A4. Basically, it is enough at the end to do the derivative with respect to A4 to obtain the optimal trajectory. At this moment, the problem is as last time, but a little bit more, I don't want to say complicated, but a little bit more articulated, because we have more conditions in the sense. At this moment, I did introduce any motor and so on. We will see later. Let me switch on the program. It would be nice to show you probably. Look, X. Exactly was what I told you. Everything is in a function of A4. Everything in the sense the polynomial, the coefficients of the polynomial, and the function of A4. Polynomial is in time, no? Because we want to, as in MPC, you remember the trajectory, the velocity trajectory which I want to track is in a function of time, related in step, each second, each millisecond, each, I don't know, it depends of many things, how I can step the trajectory. But anyway, it's in a function of the time. We have seen also in MATLAB, in Simulink, we simulated this model predictive control, which I presented over time. And what about the velocity? Here is this function diff, basically consider this expression x, which is explicitly here. We try to symbolically do the derivative. Function diff is a function with 2 arguments. The expression which I want to do, which I want to realize the differentiation, with respect to what? with respect to the time, no? Because the velocity is the derivative of the position with respect to the time. Also the acceleration, no? We can see here. In this case, of course, is the derivative of the velocity. This means what is v? Basically, it's the derivative of this expression, which the computer help us, no, to calculate. What about a is the derivative of this expression here. 8, probably we can see a little bit better. Let me see. Where is? Look, for instance, this element here is the derivative of this, no? Just to understand. Okay, let me go ahead. Then, as last time, I can calculate the force as a function of the system somehow. No? Do you remember last time we have seen very well this. And look here, what I am considering. Let me see if I can express or calculate better here. This I already. Let me see if this is exactly this example. Let me come back. Let me come back on the software, because this could be the software is some variation. Let me see again. Okay, here I have an force. A particular force. Let me look which force I have here. I have a force which is characterized, and a motoric force, which is characterized by m multiplied the acceleration. I mean, try to read in this form. M multiplied the acceleration equals force, motoric force, minus this expression here. The motoric force is what I want to calculate. You remember as last time, no? Because the motoric force depends on the states. And the states, in particular here, velocity and acceleration. Acceleration can be also considered in the possible states, but anyway, depends on velocity, acceleration, are parameterized by A4. If I remember well, it was A4. Here is interesting because I express F equals MA plus this expression here. This expression here, and now I clarify, it's a little bit more complex because I can choose any kind of friction model. At the beginning, I told you through the presentation that I can consider also just a linear friction model, KF, it was KF multiply V, which is there. But in order to show you that the problem could be more complicated, in the sense not convex, I don't consider just this one, but I consider a constant. This means a static friction. And I'm considering an expression of the friction, which is basically squared. The name of all this expression is Coulomb friction, which is nonlinear in this sense. Here, I didn't put sign of the velocity because I am assuming that the velocity are always the same direction. I don't come back. Otherwise, you remember, I told you, I don't know in which context does the even function, this means K0, And this here must be multiplied by SGN sine of V. Let me consider just one direction. This means I don't need to distinguish which direction I am traveling. The velocity is always positive. Always positive means always one direction. This means I don't have to distinguish the direction. Otherwise, I think I told you about this concept. No? That the friction force must be the friction, the model of the friction force related to the even function must be multiplied by SGN, because the friction physically is an odd function. Odd function. I don't know if you in order should be sensible with respect to the direction. But anyway, the same direction. This means I obtain, as last time, to remember the power which is multiplied. In this case, the force is nonlinear. No? Just more complicated than this one. This is the last time. F multiply V is our mechanical power. Then look, I defined here the integral of the mechanical power between Lüneburg and Hanover. Integral. INT realized in symbolic integral. If I put here C, I have the integral calculated between 0 and T1. T1 is 1 hour, 3,600 seconds. And then I have the expression, which is the calculator help us to realize these calculations. Then I have to open another file, because here, in which I do the derivative, but this time with respect to A4. Now, the derivative A4. Let me see. Um, I don't have. Strange. I don't find the final. Let me see again in the folder. Basically, I have to do the derivative of C with respect to A4, no? And then to put 0, and then to put 0. But of course, this problem here could be not easy to be solved, because we have a function and a problem, the sense, which is not convex. This means not necessarily, let me show you what I intend. Let me see if I find the software, because this is not complete. 1 second again. Strange that I don't find. Find, excuse me. 1 second. Excuse me for but I will upload the right one. No. It's not this one. I'm looking for the software. Okay. Now I think I found it. Yeah. This is the right one. I mean, also the other one was not wrong. Yeah, here F is basically linear in this case. Now, very quickly, I didn't find the correct one. But anyway, F can be also conceived. It depends of the model. Here, we can see this is linear. I can consider the divided by the gear ratio, but this is just a constant in our example. But could be also in a parameter to be optimized. This could be a nice project. Could be a parameter to be optimized. F multiply V is exactly as before. The integral of P between T0 and T1 is exactly as before. But of course, we can realize here from this that depending of the model, this is more complete, I think. No? Yeah. Depending of the model which I am considering and the system, of course, the force could be different. What I would like to show you now, yeah, I have many. Yeah, look at this. You have many things. I don't have time to tell you, but this can be understood. Yeah, the unique parameter which is free in this differentiation of this function here is A4. I would like to show you what we have here. In this convex problem, yes, the problem is convex. We have just one solution because we have a linear system. But of course, in the problem, as before, we need a numerical analysis to calculate A4. Because it could be a complex polynomial. Let me show you the other example. The other example was C, because it's already run. And then we will compare with this. C is this expression here. It's clear that A4 is just one value. If I put diff of C, the system understands automatically that it should do the derivative with respect to A4 because it's the unique free parameter, the unique parameter. Otherwise, it should be declared. Here, we don't need. If I have two parameters, you have to put diff parenthesis W or C in this case, comma, the name of parameter. For instance, A4. I mean, you can write equivalently, but the result is the same because we have just A4. No? Yeah, we can see. We can see that this parameter here, or this parameter here, is the derivative of this. Putting this equal 0, we have the solution. This means A4 equals 0. Now, of course, the problem could be more complicated. This case is relatively easy, but could be also not possible to be solved. Let me run this. I think let me look W. Probably this is the same solution as before. Let me see. Probably I didn't run. I don't know what happens. Let me look. Both have the same solution, but again, if the system, as I told you, A4 equals 0, no? This particular case. yeah, it could be nevertheless that if you have a nonlinear system, not necessarily always we have a solution, we are able to find a solution, and we need numerical methods. Yeah, of course, here the system could be extremely complicated because if I have an electrical system, then I have to parameterize the current and so on. But the solution is the mechanical solution in this sense. And then I will come back through the model at the current which I need to generate this force. I don't know if I have it here in this, but this can be done together in 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 uh, in the project. I mean, in this kind of problem, if I don't want to optimize the gears to calculate the current and then to calculate the voltage which I need to obtain the force, which is this one, in this case, because I am considering the linear form. But if I consider the nonlinear form with the Coulomb friction, formally, I have to just to add, do you remember, K0, KV multiply V, or the KF multiply V is there, and KF or the KV, KV1, or KV1 multiply V square. No? Formally, it's not a problem, but the optimization problem could be extremely more complicated. In this case, it seems to not be the case, but could be, depends on the model, because it could be that I need really a numerical method to calculate the solution, in this case, A0. In this case, extremely easy. Excuse me, A4 extremely easy to be calculated because it seems to be nevertheless the proper convex, even though in the presence of a nonlinear friction, it could be not necessarily if the system is nonlinear, we have a non-convex optimization problem. In general, yes. In general. Okay, I have a software. Now I will upload a more detailed. Now quickly I found this here software for you. Let me start with the Lagrange. I would like to show you 10 minutes what the Lagrange is. The reason is that, as I told you, basically in any course of optimization, in any, I don't want to say in any, but at least in complementary classes, in order to recall what you did with me in math, in order to recall what you did probably in other courses, makes sense to show you a little bit, but very quickly, something related to the Lagrange. Okay, let me see if I find now. It was correct. I think it should be here also something to show you about the Lagrange. Let me see. Why it doesn't open? Lagrange. Lagrange MATLAB. Okay, let me really avoid the, how possible to say, the mathematical, or I would like to show you the mathematical aspects using this slide. I don't know if it's clear enough. Have a look. The problem of Lagrange is a problem which can be formulated considering a cost function to be optimized, as always. Also today, we have seen very quickly how the cost to be optimized is the energy. Last time I dedicated more time. The mechanical energy which I need to consider in the travel between Lüneburg and Hanover, which is the integral of what? Of P, the power, mechanical power, the force multiplied the velocity. Between Lüneburg and Hanover, this means in time. And then we have seen that everything is parameterized, at least in this is in didactical lecture by a parameter, which is in a parameter of the polynomial. And then we do the derivative with respect to this parameter and so on. Of course, if the parameter is more than one, this case I didn't consider, we have to consider to find the optimus, the gradient. Now, of course, if the problem is convex, one parameter is enough. But under different conditions, or if the problem is not convex, of course, it could be also useful to have more than one parameter to find a more suitable solution. If the problem is not convex, God knows where the solution is. We can use PSO to find a combination of two of the three parameters which can represent the global optimum. About that, we can discuss together in the project. No, I don't have time, but you can understand me. If the problem is not convex, it could be useful to parameterize with more than one parameter, and then to try to find this couple of parameters, for instance, 2 or 3. We look on the search space in order to find the global solution. I don't know if it's understandable if you remember the PSO method. Now, here is another problem, but the cost function in the optimization problem is always present. Now, we have a cost function, this is an easy example. Now, to be optimized where? Not in all possible domain. We can see from this picture, this is a little bit the idea. I don't want to repeat some boring theorem from math for engineer, but the idea is to find the minimum constrained, extremely easy example, no? To this condition, x equal 1. But graphically, we can understand very well that this cost function to be optimized, extremely easy just to figure out, is in a paraboloid. Now we can see here this surface in 2 dimensions. If I do the intersection of this surface with respect to this constraint, I don't know if feasible. We have a parabola here. This means the idea is this kind of problem could be useful in constrained optimization problem, in which we have to find a minimum or a maximum, and in general an optimum, which is constrained with some conditions. Here, the extremely easy problem, x squared plus y squared, constrained to x equal 1. We can see that we have a minimum here, just graphically. In which kind of problem can be useful, this possible approach? In many problems. Just to understand for you, for instance, this is extremely easy. We don't need to do. Let me explain. For instance, we have 2 products, X and Y, per day. One company produces 2 kinds of products. And this function here represents the cost of 2 products per day. Of course, it's semi-trivial, as I told you. But the product 1 is just 1 element per day. And then we have to calculate what is the optimal production of Y in accordance with this cost function. Of course, here is we don't need to do the calculation to find in any case the solution. But the Lagrange helps, for instance, in this kind of problem to calculate Y. Of course, we apply Lagrange not in this case here in the problem more complex, extremely more complex, because we can see if you put here x equal 1 and you do the derivative with respect to y, y is equal to 0. This means the example which I told you is a little bit, but of course, if the function is more complex, if we have a constraint, more complex mean more variable, mean more products. If the constraint is a function more complex, it's not easy to find. We need this method here, which consists to write a Lagrange equation, which consists of the, let me say in a combination, let me say also linear combination in the sense I sum the function to be optimized, plus or minus it is the same, lambda, which is a parameter, multiply the constraint, x minus in implicit way, an implicit way. Why this? I don't have time in this course to tell you, but probably you remember my lecture where this Lagrange equation come from. Why with this expression we can nevertheless calculate the minimum. The idea I give you, nevertheless, the idea that in the point in which we have the optimum, in this case the minimum could be also a maximum, the gradient of the cost function is parallel to the gradient of the constraint. If you look at my lecture in engineering, math for engineer, or in general, if you remember this kind of problem, you can recall where this idea comes from. In any case, again, derivative. In our case, derivative means this gradient. We have a more than one variable. We can see that is the gradient with respect to what? X, y, and lambda. Lambda is an auxiliary variable, but nevertheless can be calculated. Lambda is exactly, if you look at the demonstration, is exactly this proportional element between the two gradients, the gradients of f of x, y, and the gradient of g of x, y. Must be parallel. I give you the input, but of course it seems to be a little bit strange with I can say without the demonstration, but at the time it is not also the goal of this. And then of course we have to put this gradient equal 0, and we can calculate. We can see here using this equation here. Sometimes this equation is not easy to be solved because in general it's not linear if the system is complex. It's not this case. It's no linear algebraic equation. This means it could be also necessary in a numerical solution. 1, 0. As I told you, y is equal to 0. And then we have to classify using, I don't know if you remember this border Hessian. Now, it doesn't matter if you don't remember this method here. I would like to say just one thing, and then I try to open the file, which we can realize really extremely easy form, at least these calculations here. The calculation, or at least what I told you today on this topic here, is just in mathematical, and the repetition of what you already know, or what you learn in my course, in more detailed form in my course of mathematics for engineer, but can be used in many applications. For instance, we not only in this, let me say, easy application in the economical or the production system, we applied, for instance, in the context of a motor, in which we have some constraints for the input, for instance, for the voltage, and of course x and y represent, of course, somehow, let me say, let me say, if x is in a possible constraint, let me say, of the states, which of course depend on the input. But in order to, if you remember why depend on the input, if you remember the model which I presented, the model predictive control, we have an equation in which we have the derivative of the states equal the states and the input. If you think about a possible discretization, we have seen exactly in MPC, how I can discretize the system. This x and y, current and velocity, do you remember in MPC? As a function of, again, current and velocity and the input. This means we can see that I can write this Lagrange function in terms of discrete variable as a function of the past state and the past input. This is a little bit what I would like to sketch, how we can nevertheless use also in dynamical systems, but of course, please consider the discretization, because the discretization somehow is an algebraic expression. Do you remember? Omega of k equals in a function of omega of k minus 1 and a function of omega of current of k minus 1, and the input was in the function of what is in the dynamic of the current. Anyway, we can realize that we can see this L of current omega lambda, in which current omega as a function of k minus 1 after the discretization is also a function of the input. This means we can define some interesting optimization problems which allows to calculate u of k minus 1. U of k minus 1. Because if I told you before, also in the lecture of the trajectory, the inputs, remember that in this case was the force, can be as a function of the states, the optimal states. Here, we have the optimal state. In this is, let me say, extremely easy example. To realize this, 1 minute really, I scroll down in software. Of course, if I have a motor, you have to discretize, as I told you, but believe me, if you want to go in this direction, it could be also interesting for me to work with you, because we did a lot also with this. We did a lot. Believe me, this is relatively easy. It seems to be now explained so quickly in the last lecture. It seems to be a little bit complicated, but extremely easy. Let me show you now a didactical example. Of course, if you consider in a motor, we have to think a little bit, but again, we have to discretize, no? In order to have an algebraic expression. Because do you remember, again, current of k is in a function of current of k of time k minus 1, omega time k minus 1 in forward, no? Discretization and u of k minus 1. This means you can understand that the discretization transform also the dynamics in another form. Let me, 2 minutes. No? Yeah, we can see an elector of Lagrange, but this is quite boring if I had more time. But it's not necessary here. Let me see one of this, Lagrange. Yeah, look, this example is a bit, I don't know if I shared. I will upload also my lecture of Lagrange, which I always in mathematics for engineers, but again, probably we can go in depth in the project, because the lecture belongs to math. Here, nevertheless, I try to recall quickly. Look at this. This function a little bit more complicated, in which we have a constraint, so more complicated. We cannot do directly the calculations. I define here the Lagrange function, minus lambda multiply f minus lambda g. Here, of course, I have to define symbolically x, y, and lambda. And then I do the gradient. Here I did using the diff. We have also a command, the compact command grad, I think, or the gradient, I don't remember. But here I can see I do the derivative with L with respect to x. I do the derivative of L, the Lagrange with respect to y, and then I put everything. Excuse me. I did also the derivative of L with respect to lambda, this help variable, and then look. I use again the function solve. If you want to go in depth on the function solve, please digit help solve, and then we can see also the possibility which this offers, but it's extremely easy to see. We have a function in which we can consider the three variables which must be put equal 0. and I solve the problem this, with respect to x, y, and lambda. In this case, I don't think that you need to specify the argument of the system because we have just x, y, and lambda, but just to show you a little bit more options. Solve understands that the system characterized by the expression the L, the x, the L with respect to the y, the L with respect to lambda, the LD with respect to lambda, the L, excuse me, with respect to the lambda, is R equals 0. And I store the solution in x star, y star, lambda star, exactly which I did in this slide in which I summarized very quickly the Lagrange. Again, lambda is an help variable which state the parallel between state that the two gradients, the gradients of the surface and the gradients of the constraint are parallel. It doesn't have a physical meaning in this sense. It's just a help variable. And then, of course, we can see here that I can build the matrix of the bordered Jacobian. The Jacobian basically is the matrix in the sense Hessian, excuse me, the Hessian, the border Hessian. Is a matrix which states the second derivative. I don't know if you remember to classify minimum, maximum. Now, we found a candidate point. I forgot to say before, a candidate point. The point was 1, 0. And then we have to classify as maximum, minimum. If you remember in high school, this was done using the second derivative, or the second, the third, and so on, depends. Yeah. And here we have two variables, better to say three variables, but the meaning is the physical meaning is related to two variables, and you have to build a matrix and to judge about the determinant of this matrix. Of course, could be heavy if you do by hands, but with this software here, once we build this border Hessian, basically it's an Hessian calculated on the border, because I remember that the problem consists of finding an optimal, minimum, maximum constraint, border. If you look at the picture which I presented at the beginning of this part of the lecture, we can understand what I intend of the border. Exactly this parameter. And then we look if positive is negative and so on. Exactly the same as we did in the high school with the second derivative. Let me think if I forgot to say something. Of course, this part of the lecture is explained extremely quickly. But again, if you want to work on this topic here, I have interesting projects, and we will reconsider based on this very short introduction. The idea is to show you that we have also this possibility to recall you what we did in math for engineers or in different courses. The idea is I have an interesting problem in the fields of motors, in economics too, but I am not expert, but I can assist you in economical systems to build exactly this structure here, but extremely easy, believe me, Lagrange, border Hessian, and so on, to discuss about the classification, why this border Hessian is not singular. This means the determinant is positive or negative. This means the classification is it's done without considering more derivative. I don't know if you remember, no, because it's 0, we have to proceed with the derivative. But anyway, we can select some interesting problem in this frame here, which should be already known. Therefore, I didn't tell you many things, but also in particular in technical fields, I can help you because we apply many times also with some publications. Okay, now I am closing this lecture, and with this lecture, I would like to say we can close the course. Some aspect will also the last elements. The last topic is just a sketch, but I have an interesting project on everything which I told you during the semester. And for the examination, you can consider also a different, let me say, tool in the sense, algorithm. Very important that we have an optimization problem with its convexity, not convexity, everything which I told you. You don't have to select exactly what I told you. The idea was to give you the possibility to understand how, in general, no, considering some aspects or some problems also, we can how we can use this or how what is an optimization problem. This means if you have a different algorithm or so different project, very important that we have something to be optimized. Okay, let me close now the lecture. I am here to discuss projects also today. I would like to say for the rest of our meetings, at the beginning, I would like to prefer to meet you in the presence, but if it's not possible, we can do also per Zoom. But typically also once could be nice, also now, also next week. But if it's not possible, we can also meet per Zoom. Okay, nevertheless, thank you really also for this lecture of today, even though it was a little bit, informal in the sense very quickly explain some aspects. But we can really go in depth with the project. Again, with these complementary courses, I obtain a lot of interesting results, believe me, because the course go ahead also through the project. This is a little bit also the idea that we can interact. We can interact very, very often, and as oft as you want. Thank you.